The human mind, in contrast, has, instead of just one pathway forwards, it's got a number of different pathways. So as soon as information hits the visual cortex, it starts exploding down a series of different pathways, each of which emphasizes different kinds of information. So you can do the same thing with VAEs.
I think right now we don't really have a good way to evaluate if these language models understand language. I mean, they're good at solving the practical tasks we want them to solve. But then for more challenging tasks, like communicating with people or understanding humor, these models are very brittle.
Perhaps this is even more cynical than Paul. Your take is that perhaps the language is really nothing but just one layer or the shared weight across all those neural nets that we have in our head. Maybe that's about it, right?
My wife is a neuroscientist, and she completely disagrees that it's anything like attention, real attention. But I definitely think that the inspiration is certainly similar in terms of what we're trying to do with the model.
This is Brain Inspired.
Hey everyone, it's Paul. Welcome to the fifth installment of the Neuromatch Academy panel series here. This is the second of the deep learning series. This week was about doing more with fewer parameters. So I guess convolutional neural networks were covered, recurrent neural networks, attention mechanisms and transformers, and generative models like variational autoencoders and generative adversarial networks. With me today are three people from NYU, João Sedoc and Kyunghyun Cho. They're bringing their language model expertise to the conversation today, among other things, and Brad Weibel from Penn State University. So we don't talk a lot about convolutional neural networks or recurrent neural networks, but we do talk about variational autoencoders. Brad talks about his work using variational autoencoders as a model for building latent representations for vision and memory and possibly imagination and other things you'll hear about. So we spend some time talking about that, and then we spend a lot of time talking about language models and the idea of attention and the story behind how it became called attention. We also get into how everyone thinks about the levels of abstraction when dealing with language models that can take in letters or words or sentences and so on, or pixels. So there's that. We go down multiple other roads. It was a really enjoyable conversation. You can go to the show notes to learn more about them at braininspired.co/podcast/NMA-5. Okay, enjoy. So I'm here with, three language modeling experts and one non-language modeling expert. And we'll find out more about each of you. So the first thing I'd like to do is just go through and ask each of you to introduce yourself briefly. But then for fun, I thought maybe what you could each say is a piece of work or an idea that you think you're best known for. And then maybe, and it could be the same answer, then another idea or piece of work or, a body of work that you are most proud of. So, Kyeonghyun, do you want to get us going?
Yeah, sure. Let's do that. Yes. So, hi everyone. I'm Kyeonghyun. So, I'm an associate professor of computer science and data science at New York University. I've been here now slightly over 6 years, and I work mainly on how to design a machine learning algorithms for natural language processing as well as machine translation. Although, recently I've been going through what I call research identity crisis. So I've been actually dabbling here and there, including a bit of biology, a bit of chemistry, a bit of physics, and so on, without much success so far. But that said, so I was asked to talk about the most well-known paper of mine is probably the attention paper, where we introduced the attention mechanism in the context of the neural machine translation. But the one that I'm most fond of among my papers is paper from 2013 or 12, if I remember correctly. That was kind of final paper I wrote for my PhD dissertation. And then back then, it was the kind of final phase of work, a lot of people working on Boltzmann machines. And in particular, the last flame was the deep Boltzmann machines. I'm pretty sure there's only about 5 people in the world who have actually trained deep Boltzmann machines. And then my final paper in my dissertation was about how to train deep Boltzmann machines more easily by pre-training in a very non-trivial way. And then I got that idea out of a bus ride in one random day. So I'm very fond of that idea. No one ever reads the paper, not even my students. So no one really knows about it, but my favorite. Yes.
Is it a thing where you remember where you were in the bus or on the streets and what you were doing, etc.?
Yep, precisely. I was on a bus going from Espoo. That's where I did my PhD in Finland to Helsinki during the day. I think it was on Sunday, actually. Yes.
Nice. Really? No one's working on Boltzmann machines anymore? Really?
None that I know, or at least not me.
Yeah. Oh, very good. Who would like to go next? Brad, do you want to take a stab at it?
Sure. My name is Brad Weibel. I'm an associate professor at Penn State University in University Park. I'm also one of the founders of Neuromatch Academy. My work primarily involves understanding how the human mind builds representations of things that we see. And I guess the work that I'm probably best known for in my little pocket of the field is understanding the temporal dynamics of visual attention. So on a time scale of below 1 second, like 200 to 500 milliseconds, how does attention shift on and off, not in an oscillatory way, but in a sort of aperiodic way to sort of capture the inherent statistical structure of input that we're taking in. And so I think the paper there that is kind of most interesting, and the one that I sort of think the most highly of is published in 2009, and it's a computational model of the temporal dynamics of attention. And what stands out about that one is that the sort of structure of the attentional system in the way that it works. I programmed it, and there was a parenthesis error, and I actually put a multiplication on the wrong side. And that actually solved the problem that I was trying to solve.
Oh, gosh.
And I had to then go back and figure out why was this working so well. And then the light dawned, and there it was. Just advancement, innovation by mistake.
Yeah. Yeah, that's the best kind. I didn't say this before, but you're the only non-NYU person here, I believe.
That's right. Yeah.
But, close enough, like the neighboring state, right? Yes.
Yeah, that's right. Yeah, we're all East Coast here. I actually started my undergraduate degree. I'm in a psychology department now at Penn State, but my undergraduate degree was in computer science at Brandeis back in the early 90s, which was at the sort of dawn of the AI winter that really sort of crushed things. So like that was the sort of last gasps of the old symbolic movement were sort of in full swing at Brandeis when I was there. So like thinking machines, for example, was in the process of folding. And we had like thinking machines mugs in the department. I was trained on Scheme and Lisp. Everything was about like ab strips and strips planners. And so this was all before deep learning. And after that, I went straight into hardcore neuroscience. I was implanting electrodes into rats for my whole PhD career. And then I sort of have looped back around after a very long time to be sort of relearning the fruits of this new deep learning revolution that we're all sort of experiencing. So it's really been a long trip.
Are you relearning with it begrudgingly, or is it a new and exciting thing, you think?
No, it's really fascinating. I'm a skeptic and a curmudgeon at heart, but I can't help but enjoy the really interesting things that we can do. And in particular, after spending so many years building computational models that sort of operate at a very abstract level, where you've got like, this is the neuron for the letter A and the neuron for the letter B, to build networks and models that actually deal with real world stimuli, like images and et cetera. Like, I think that's going to be a real game changer in allowing us to break out of the sort of traps of low dimensional thinking that a lot of us have been in for a while. Because, if that's all that your model can handle, then, it's difficult to build intuitions otherwise.
Nice.
So yeah, it's been great. I've been really enjoying this.
Yeah, I didn't realize you had the GoFi background, the symbolic AI thing.
Long time ago.
Yeah. You're another NYU language expert, and I'll let you tell everyone. I was going to tell everyone who you are and what you do. Why don't you do that for me?
Sure, I can go next. So my name is He He. I'm currently assistant professor at NYU computer science, same as Kyeonghyun. So my current research is mainly focused on neurotext generation. And since I started the faculty job, I also branched out a little bit and also working on how to make our natural language understanding models more robust nowadays. And I think the work I'm most known for, if you look at the citations, are probably my work on neurotext generation, some less common applications, including textile transfer and Pong generation.
What is that? Pong generation? Sorry.
Generating Pongs, like.
Oh, Pong generation. Gotcha.
Yeah.
Okay.
That was a fun project. The work I like most was when we built a dialogue agent that can actually collaborating with people and solving some puzzles. So most of the dialogue engines are, if you look at this task-oriented systems where they help people to book restaurants or movie tickets. But I thought that project was very fun because we actually designed a model that can reason about the need of the human partner and take initiative to give them information they need to complete the task together. And recently, we also, went further down the lines of this human model collaboration, where we try to develop text generation models that can help humans writing more creative text. So I guess I've been always interested in this aspect of how can machines better collaborate with humans and help them be more productive.
So bots, you just want to fill the internet with more bots, right?
Not bots that are replacing people, but helping people.
Okay, I know that's what they're supposed to do, but then don't they sell us stuff? I'm not trying to argue with you, but I think bot has a negative connotation in my mind, but I think you have a very optimistic outlook on it.
Mm-hmm.
Yeah, I think they. So sure, there are negative aspects where it's possible that if we just have bots learning freely online, they could generate very unsafe or toxic comments. But I think if we, try to build bots that can help people. So it's tricky to find the right application where the bot can maximally help humans to improve their productivity.
Hey, Paul, can I also ask some questions on the way?
Everybody, please jump in and ask questions. Yes.
So, I had actually one kind of conflicting, let's say, message I hear here is that, okay, so you work on the pun generation. And so pun generation is connected, let's say, having fun, being creative and so on. And then you talked about, helping humans be more productive. But isn't like the having fun and productive kind of opposite notion? And then, can machines actually help us doing both? Or, does it have to choose one of them? I want the machine to choose fun, but I'm pretty sure it's easier to optimize the productivity, my guess is. What do you think?
So by optimizing productivity, so I don't think it's conflicting. So they can, I say, by making people more productive, we're making humans working more as opposed to
having fun. As opposed to having fun, yes.
Aren't they the same thing, though?
Yeah, exactly. It can help you to complete your task in a more fun way, I guess.
Okay.
I mean, it would help with motivation for sure, right? I mean, if you get people to enjoy their workplace environment.
Mm-hmm.
Yeah, so I guess we want to move the tedious part to machines and let humans focus on the more interesting part of the job.
João, you share with Hoa the an appeal to conversation with machine. What is it called? Machine conversation? Machine. What is it called?
Conversational agents is what I
conversational
agents to call it these days.
Who are you, João? What do you do, and what are you most proud of, et cetera?
Yeah, so I'm an assistant professor at NYU, but in the Stern Business School, in the technology operations and statistics department, particularly the technology subgroup. And yeah, a lot of my work focuses on conversational agents and a lot on evaluation of them. I think I'm probably best known for evaluating conversational agents and doing a lot of work recently on evaluation. And, my focus, the business school aspect of my focus is really more on understanding how these conversational agents, how to use them properly within business. And particularly, I'm interested in healthcare and public health. So I do a lot of collaboration with people in public health. And so that's probably what I'm best known for. Okay, I'll answer in two parts. The first one is what was the most fun. So the most fun project that I've worked on, so I worked on some work early in my PhD on spectral sign clustering.
You have to describe that very briefly. You have to describe that, please.
Sure. So there's this work on using taking the similarity between different items and then figuring out how to take that similarity matrix and use the most common features using singular value decomposition to cluster items together. The signed part is figuring out how to incorporate opposing signals. So instead of similarity, dissimilarity into this matrix, and then cluster. So that's what's called the sign spectral clustering.
Okay.
But the fun part about that, so the sign spectral clustering is cool, but the fun part is one of the biggest problems that I see all my friends having is figuring out how to assign people to tables in a wedding. And so I worked with a friend of mine on actually figuring out how to change this sign spectral clustering into a constrained way in order to figure out the wedding seating problem, which is you have a whole bunch of people, family and relatives. Some of them know each other and like each other. Some of them don't like each other, which happens, unfortunately. And then how to actually figure out how to seat them. And it's one of those things where people spend a ton of time, and there's we actually built a web front end, which unfortunately we didn't have time to finish, but we have if anybody's ever interested, we've got an algorithm and some code to actually tell you, in some theoretical way, how to actually do your wedding tables.
So where do I put
Joe, how do you, sorry,
Please,
Paul,
no,
but how do you evaluate it? I mean, you work on evaluation, you said, but have you actually evaluated your algorithm for, actual weddings and then see if people were happier or, angrier or whatnot?
So it's a really good question. We never got to that stage. I mean, what we can evaluate is how many people that don't like each other sit together and how many sort of reject tables there are, which end up being the people who are isolated nodes in our graph. We never got to the evaluation component because we never actually, I think there was one friend that used this for, just like a corporate setting where people had tables and they didn't want certain people in groups to sit together. But yeah, it was fun. It was just fun. And we used, Buffy the Vampire Slayer as characters in that as an example of so it would work. So it was all silly, but it was great. It was a fun paper. It's on archive. Okay, so stuff that I'm most proud of. So we have a set of work on essentially medical question answering, which is some of which is published, some of which is now unpublished. And what we're trying to do is figure out with these young women in Uganda how to build conversational agents that can help telemedicine people to actually help young women with questions about maternal health. I love the very theoretical side of my work, and I really enjoy doing the applied side. And so some of those stuff that I like the impact of actually, helping people.
I wish I knew what that was like. So, all right. So very good, everyone. So part of this week's materials, I believe, were convolutional neural networks and recurrent neural networks. And I don't think we're going to talk much about those because that's not where everyone's expertise. Well, I mean, I'm sure everyone's an expert in those as well. But, just to briefly mention them. So the deep learning, quote unquote, revolution in 2012 with AlexNet happened. And that was a convolutional neural network. And since then, those have become standard for vision and lots of other things. But, I guess I would like to know So the story is that's when the revolution happened, and that's when everyone realized, oh, deep learning works. Is that the story? Like, what was your experience when the error dropped by, I don't know, 6%, and that was huge. It was probably more. I don't remember the exact percentage. It was a large percentage drop in the error on the ImageNet data set. And in your worlds, were people throwing confetti and saying the revolution is here? Or what was your experience? Because Kyeonghyun, you were working on restricted Boltzmann machines, for instance. So
yeah, that was a mistake. So in 2012 summer, there was if I remember correctly, 3-week-long summer school hosted at UCLA, the IPEM there, on deep learning. That was hosted together with the CFAR and so on. And then Jeff Hinton was one of the speakers. There were about 40, 50 students. I was one of them. And then Jeff actually broke the news about ImageNet there at one of his lectures. And then, everyone was sitting there. And then as soon as Jeff talked about it, and then at the end of the day, it was really just a convolutional network and dropout, right? So dropout was a big thing. So and then there's nothing much to explain. So as soon as Jeff says something about it, and then he started talking about, I have some intuition. It has something to do with the evolution, biological sex, and so on. Everyone lost interest, and then they all started to code it up because dropout was so easy to implement anyway. And then people started implementing it. So in some sense, it was very surprising to all those students who were actually working on these restricted Boltzmann machines, the convolutional net in a very limited form, or the sparse coding and so on, that all the things that we were working on as PhD students or postdocs or whatnot actually were working, except that all you needed was a bit of, the magic here and there. In some sense, we were building everything toward this moment. Just that, the Jeff Hinton and, the Alex Krzyzewski, Suskever, they kind of came up with a couple of tricks that pushed the whole thing. So it just tilted toward this success side. So, yeah.
Because one of the things that restricted Boltzmann machines were good for was, stacking them was doing basically an unsupervised pre-training that then you could stack the model, pre-train it, and then it would all of a sudden become a good classifier with a little fine-tuning from back propagation. And so is that what you were talking about, that you guys were working toward that?
Yeah, I was working toward that. A lot of people were working toward that. But the weirdest thing is that, like the Jan LeCun, Jan was able to train this reasonably deep convolutional network already in early 90s, mid 90s, but somehow he couldn't actually scale it up because there were just few missing pieces. And then that's why we had to take all those, the long tour, they tried to come up with a restricted Boltzmann machine, how to train it, stack them up, fine tune it, and so on. But at the end of the day, it's probably not revolution, but it's more like, let's go back to, I guess, 90s. I think Brad, you were referring to the beginning of the winner, and then just realizing after about 15 to 20 years that we actually had a lot of solutions or the answers already back then, just needed a couple of the, let's say, tricks that's going to tip the balance toward the, let's say, summer side rather than winter side. That's how I view it. Yes. And then Brad, you probably knew the answer already in some sense, like 99%. Just Jeff had to come up with dropout, I guess. Yes.
I think that's one of the most challenging aspects of deep learning, which is that success involves not just having a good idea about how to do something, but also a lot of time and effort spent doing the fine tuning to get it there. Right. And it, I'm from the sort of bespoke modeling side of comp neuro, where we design these sort of handcrafted neural circuits where this neuron talks to that neuron with a connection weight of this much. And there progress is a lot more rapid because you have an idea, you can implement it, your intuition can handle it. But on the deep learning side, it seems like there's this extra barrier of a lot of hours of elbow grease spent working the problem in order to make your good idea, or even to test if your good idea is actually a good idea. So I think that's one of the challenges there. And I think it in some ways also a barrier to, smaller labs and smaller groups, especially those with less funding, because you just really need that extra time.
And Brad, why, before you finished, did you have that sense? Was it a clear demarcation that deep learning is here, or what?
I was living in a different world at that time.
Okay. Yeah,
I was completely oblivious of all of this stuff at 100%, not until I don't know, maybe 6 or 7 years ago did I start tuning into things like this.
Yeah. And João, what do you how about you guys? Have you even worked with models that aren't deep learning models? This is a terrible question to ask, I realize.
Yeah, I can provide some of my perspective. So the first time I learned about neural networks was in undergrad, where I implemented backpropagation in MATLAB. And then I started my grad school in 2011. At that time, I think for computer vision, maybe people are already accepting that neural networks is really the next big thing. But for NLP, I feel people are definitely not early adopters, at least in my lab. Like we were still using support vector machines, large margin models, and not neural networks until maybe 2015 or 2016. And I think as Brad and Kyeonghyun mentioned, I agree that for the pioneers like Jeff or Young, they had lots of trouble. They have to come up with some tricks to make this neural network work. But I think by the time of 2012 or 2014, for downstream applications, there are already some well-documented practices or tricks that can make this model work. But somehow at that time, I think, so in retrospect, I think that was a misconception, because my impression was at that time when I was a PhD student is that it's extremely difficult to make this model work. But when I tried it for the first time in around 2015, it's actually not that hard. I tried a set of hyperparameters and it just works as in other models. So I think that actually slowed down people's adoption of these neural network models in NLP. And there are other blockers where, some people don't think that it's interpretable or reflecting any properties of language, so they may not work as well. But it turned out that these models are actually way more powerful than the symbolic models we used to use.
Oh, you're welcome, huh? Yes, I think I contributed a little to make it easy. Yeah.
Thank you, Kyeonghyun. I'll say it. João, what was your experience?
Yeah, so I think a lot of my experience came from, doing machine learning, I guess, in another field and sort of transferring over to natural language processing when I started grad school. So in finance, it was all about feature engineering. And feature engineering at the time was like the thing that I knew how to do and support vector machines and kernel regression. And then, I moved into more of the hidden Markov model world, which I still love, but is now completely supplanted. I saw the full sort of spectrum of supplanting of HMMs by, these recurrent models and then transformer models. And I think, to some extent, seeing that happen, it when, sort of the sequence to sequence model came out at NeurIPS, everybody was like very interested in it already, like the fact that it works, and why do you need to reverse these things, and all of those components. And I think I learned like 6 packages along the way and re-implemented 5 times. And now I see the grad students that I work with, install a package and things run, right? So, I do agree that for very hard problems and like new things, there's still dark magic of like making stuff work in deep learning, but at the same time, there's a lot of time that's not spent on feature engineering, which is partially a little bit problematic because I find that, my students tend not to look at their data, and feature engineering really requires you to look at your data. But at the same time, I mean, the representations are just more powerful.
Another memory occurred to me, which is that when I was in high school, actually, that was when I was playing around with neural networks, and I was trying to get a backprop network to learn how to recognize characters, and I couldn't get it to work. It was just like failing every single time. And this was me running into that wall of sort of not understanding that you can have the algorithm correct, but there's some underlying problem in the way it's set up. And so I called Jay McClelland in his office from high school and said, I called him on the phone just to say, like, could you help me with this? And I described the problem, and he was great. He basically like encouraged me to, double check the algorithm and, et cetera. Like, I mean, what could he do? Like, I mean, I'm just,
but the fact that he spoke to you, because,
he answered the phone, right? It was great.
That doesn't surprise me. I've talked to Jay, and he seems like that kind of guy. So that's great.
Exactly. Right. So anyway, so I couldn't get that model to work no matter what I did, and that's why I went into symbolic processing. There we go.
All right. So maybe let's start off talking, because I have a feeling that we're going to end up talking about natural language processing a lot here. But part of the week's materials covered generative models like variational autoencoders and generative adversarial networks. And Brad, you use variational autoencoders. Well, you've started using them. I mean, you used these. I'm trying to think of what kind of models did you call them? Bespoke.
Right.
Yeah, I'm trying to think of someone, a well-known brain neuroscience researcher, talks about the cottage industry and how it's important in neuroscience to have like these small labs that are doing these experiments that are fairly small, rather than the big collaborative multi-lab collaborations where everyone's using big data and big models and stuff. And so you've kind of you've come through that bespoke cottage industry, and you're still there, I guess, but now you're using the variational autoencoders to do what?
Yeah, so it's sort of a new direction for me. What we're trying to understand is how we can use variational autoencoders to build good latent spaces to understand how working memory might be stored in the brain. Right. So working memory is thought to be like a keystone of our sort of larger abilities to think and reason, because it lets us hold on to information in very flexible ways and access it and manipulate it. So what you can get out of variational autoencoders, at least if you're just going to, for example, look on the vision side, is a way to build a series of latent spaces that let you store information at various different levels of compression, if you will. And so why that's useful is that when people remember things that we experience, I can show you something that's completely novel, like a shape that you've never seen before, and you can build a memory of that. You could even draw it, in a generative sense. But also, if I show you something that's familiar, you can more easily remember it. So there's some advantage of that familiarity. So what we've been doing is taking VAEs and using them to build these latent spaces, and then constructing memories out of subsets of those latent spaces in a way that would be consistent with the task you're performing, right? So if you see something, you can build a memory of that thing, but you do so in a way that serves what you're trying to do, right? So you might be focusing on the visual details of like a car. You might focus, you might remember that it's got a dent on the fender, or you might just remember that it was a car of a particular make and model. And so you can sort of have a memory that sort of runs the gamut of being anywhere from the sort of low level visual detail to the higher level conceptual category, or some combination, right? You can have a memory that is both the sort of conceptual content blended with the visual details. And so VAEs give us a nice way of having a series of staged latent spaces, and you can build a memory by combining different parts of those latent spaces, storing that information, and then reconstructing it back into the latent spaces. The other really nice thing that we can do with VAEs is that we're playing around with. Right. So, in the typical sense of these models, you've got like a single pathway, right, where each space sort of feeds into the next one. Even like a ResNet 50 is basically like a big line of these things. But what you can also do is this sort of goes back to like the bespoke thing where, the human mind, in contrast, has, instead of just one pathway forwards, it's got a number of different pathways. So as soon as information hits the visual cortex, it starts exploding down a series of different pathways, each of which emphasizes different kinds of information. So you can do the same thing with VAEs, so just as an example, what we're doing right now is just, we've got this VAE and we pull apart the shape and the color information from a stimulus. So we've got one of the bottlenecks that is only trained to represent color information, and the other is trained to only represent shape information. And we do that by having two different objective functions. So the information basically flows through one, and then we train it, and we zero out the gradients. So if we want to train on color, we zero out the gradients for the shape side. And if we want to train on shape, then we zero out the gradients for the color side. And the VAE basically learns to separate that information to different representations and then merge it back together again.
Don't you have two sets of latent spaces to do that with, to channel it through?
You do, right? You've got so imagine a VAE where you've got like L1 and then L2, and then the bottleneck is actually two subparts. But then they merge back together again at the fourth layer and the fifth layer. So the VAE basically learns to split the information, then merge it back together again. And it's really interesting because this is taking us down pathways of thinking about how imagination and visual imagery works. So your ability to sort of imagine combinations of things. So we can tell this VAE, I want you to imagine a red 2, and it will generate a red 2 for us by we activate 2 on the one side and red on the other. But what it can't do is it can't imagine or generate combinations that it hasn't seen before, right? So if it's seen 1, 2, 3, 4 in blue and 5, 6, 7, 8 in red, it can't do a 2 that's red. And so this sort of gives us some pause to think about, well, maybe the purpose of imagery is to sort of develop ways to generate those combinations you hadn't seen before. So the encoding pathway maybe doesn't have that ability. It's never experienced that particular stimulus before, but the decoding pathway might be able to nevertheless give it to you. So there's a lot of really interesting ideas that we're having, just starting from this working memory model, and now starting to think about imagery and imagination.
So, Brett, I have actually one question along this line, because this is the problem of the compositionality and the systematic generalization in some sense, right? So the one thing that we've run into as in the natural language processing research, in particular, actually, Hall has been actually looking into this quite a lot, is that there seems to be a kind of fundamental limitation that comes out of just observing a static data. For instance, the one example that I always use is that when we train a machine translation system on a small, let's say, corpus, and then let's say somehow in that corpus, the word banana always appears after the word yellow. And then can this machine translation model be able to translate green banana correctly? And then if so, how can it actually disambiguate the fact that the yellow is a color and does not actually determine the property of the object that is the banana, right? And then you're statistically saying, I don't think there is a way forward, and then there has to be some kind of, I guess, the role the bespoke models actually serves here, because it seems like the data alone is not enough. Have you actually, and then I think you're actually touching upon this, right? So if you have the separate channel for, say, colors and shapes, then perhaps it's going to learn. But what you're saying is that it still can't learn the kind of new combination. Is that what you meant?
Well, at least the straightforward VAE architecture cannot, with fully connected networks. But I mean, if you were using transformers or something else, which had more flexibility, perhaps you might be able to do that. But yeah, with regards to the bespoke thing, right? So we're sort of assuming here that the brain would have these pre-existing differential objective functions to encourage that information to bifurcate into different pathways, right? And that's the sort of not data-driven, but perhaps, well, I guess you could say it's not data-driven within the lifetime of the organism, but perhaps data-driven on the species level, right? In terms of designing how that works.
Actually, a follow-up question. Sorry. So a follow-up question is: so here are the model automatically learning what are colors, what are shapes, or it has to be you have to tell the model that okay, here's the coloring part in the image.
So the stimuli that we're using are really simplistic in that they only have one color. So if you can imagine like MNIST digits, but they're just like colorized to be one of several colors. And the objective function that we use sort of enforces it to learn about color or shape. So to enforce it to learn about color, you just collapse all the spatial information together, and you're just learning the RGB of that stimulus. And to learn shape, you collapse across RGB and you just train it to learn about the shape information. So in that sense, the distinction between shape and color is baked into these bespoke objective functions.
Right.
Which, I mean, is not completely crazy. I mean, the brain has a lot of very unusual ways in which it can process information. I mean, the VAE is also a really interesting way to think about how vision is organized, because you go up to the bottleneck and then, instead of going forwards from there, you can think of it as actually going back down the visual pathway, right? So you go from V1 to V2 to IT cortex, but then the return pathway is from IT back to V2 and then back to V1. So in actual fact, the first and the last layer of a VAE, you would think of those as both being within visual cortex, just perhaps on different layers. And it's really easy then to imagine, from a biological perspective, how you would do the objective function, because the neurons are literally sort of next to each other by the time you go from L1 back to L5.
That's one pathway, but like you said, I mean, the brain is just this huge explosion of diverting pathways. So So you'd need a VAE there, and then another one to go forward and then sideways and all which way.
Yeah, right. You'd also have one, for the auditory stream.
Sure.
Yeah, so like for the auditory side, but also for motor and proprioception, you could easily imagine a similar kind of mechanism there. Each one of these would sort of build an organized set of latent spaces, perhaps with some genetic predispositions to sort of divide things in certain ways. So there's this huge debate in our field, for example, about whether the fusiform face area, which is a brain area that lights up in a magnet in an fMRI when you see faces, like is that genetically preordained to be a face specific brain area, or is it just that is an expertise area that tends to end up focusing on faces because that's the thing we tend to become experts in? And so there's this huge debate about whether or not that is genetically preordained or whether that's an outcome of the data that we experience. So you could imagine also like a sort of objective function that is geared towards faces, that sort of like emphasizes that only face information gets processed through that bottleneck. And then you could combine that information. Then, basically when you're experiencing something, it would be a conjunction of different latent spaces, right? You've got one latent space that's specialized for faces, another for certain kinds of shapes, colors, etc. But then you think that the information travels forward, it bifurcates through all these pathways in different latent spaces. But then when it comes back to V1, that's when you're recombining all that information back together again. And that would be the process of visual imagery, the sort of reconstructing in your mind's eye what something is. And then, you can ask other really interesting questions about to what extent does someone's phenomenal experience of visual imagery tell you about what's going on in that machinery? Is that epiphenomenal? Or is that indicative of a fundamentally different way in which that return pathway functions? Yeah, so a lot of really interesting questions there.
I don't know, just listening to this, it's really fascinating how much we know about how human brain processes this visual information as well as auditory information, and then how Brad, you were able to actually explain this complicated process, I presume, in a very succinct and also probably the precise way, how we get the abstract level. And whenever I think about it, and in the context of the natural language processing or the language processing in general, I'm just not even sure, where we should start, in the sense that we often start with the text in natural language processing, but clearly what we see as humans is not really text. We look at every single pixel of the strokes or whatnot. So how do we actually get to that kind of abstract level? Or is language actually abstract, or is it actually even more low level than we imagine that is? And then what is the right kind of, let's say, should it get compressed over and over? Because the weird thing is that these transformers or the LSMs or whatnot that we've been working with, the input tends to be much lower dimensional because we always use one-up vector. But then we kind of blow up the dimensionality enormously as we go over and over the more and more layers. So I don't know, what do you think, right? Can the explanation you gave be made analogs to the language processing in brain as well? Or is it something completely different?
Yeah, so I guess I would say that the best way that I would advise to approach it is to think that there might also be different latent spaces on the vision side of language processing, right? So you might have some latent spaces that focus on the shape of the word, like the outline characteristics, which we now think is one of the ways in which people recognize words quickly, and another pathway that emphasizes the letters, and maybe another pathway that emphasizes combinations of letters. And sort of all of those are working in tandem, not necessarily in sequence. And so the outcome that you get is a product of those things working in parallel.
The vision system is one system in the brain that we probably know best of all the brain layers and the anatomy connections and representations that are in there. All the other ones are catching up as well, but language is still pretty elusive. And, so the attention mechanisms in language that led to the transformer is just so powerful. And there's work being done to see, is this how, when we use a language model like that, train it on Wikipedia, the corpus or something, and then look at the structure of the language, there is some linguistic structure that it comes up with, but on the other hand, we really have no idea how language works in the brain, right? So I wonder how working with language, and Kyeonghyun, you were just talking about the different levels of abstraction, and I was going to ask about this anyway. Because the transformers could be used for the lowest, at the pixel level, right? Or at the word level, or at the sentence level. And I'm wondering how you NLP folks, and especially, once you get into like the conversation with the, I was going to say evil bots, the beneficial bots, with the conversational agents, how you guys think about language and how working with the language, training these models has made you, has sort of altered or changed your mind at all about how you think language works in our minds and or brains.
Right. So since I haven't really worked much about with the conversation, I'll start with a much smaller unit, and then I'm going to let her and Joel kind of take a much bigger view into the idea how language is, because at the end of the day, language is a communication medium that probably sets this apart from many other modalities that we think about, like the visual or the auditory and so on. So when I started working on this particular, let's say, machine translation problem in 2013 and so, everyone was looking at the sentences as a sequences of words. So we built a neural translation system, just like how the existing statistical translation systems are built, by looking at the sentence as a sequence of words. But then what I realized is that I was implementing the whole thing. We were running all those experiments, and then we realized that wait, hold on, all my neural net sees is literally a sequence of integers. It's just an integer sequence where the integer just refers to the index in the vocabulary. So we're like, perhaps it doesn't have to be words. And then you had, of course, people who had more experience working with the natural language realized that you just replace it by some kind of simple segmentation algorithm to have some kind of subword vocabulary. It still works, and then it actually works better because we get a much more compact, let's say, vocabulary. And then we're like, perhaps we can just work with letters. So initially, what I did was we're going to use the input, a sequence of words, but we're going to ask a neural net to generate the translation as a sequence of letters. And then it actually worked beautifully. And then the attention was able to attend to the relevant words for each letters. So there was a huge discrepancy in the levels of abstraction between, let's say, letters and words, but still the attention was worked as well as before, because it was all working internally. And then that's when we realized that perhaps everything could be just letters. So we built the character-to-character translation model that actually worked pretty well. There were some computational issues, but I did that aside because I'm pretty sure Google can always solve it for us anyway when it comes to computational issues. And then, what people at Google indeed worked on was that perhaps we can just work at bytes or perhaps even bits. So there were some papers just showing that we can actually work with bits or the bytes or the Unicode bytes, and then still the models tend to work pretty well. And then this actually does tell us a lot about what kind of, let's say, abstraction that these neural nets can make out of, let's say, really nothing. As in, it's just a sequence of integers at the end of the day, and it's going to build up some kind of representation. Of course, whether those representations are meaningful, let's say, externally, is a different story, but I think that's what we have seen. And then that's the reason why I asked this question initially to Brad, is that what is the right level of abstraction to think of language to start with? But I'm pretty sure it gets much more complicated when we think about conversation. How, Joel? I'm pretty sure you can tell us more.
Yeah, actually, one follow-up question / comment on what you said about the character-based models versus like word-based models. So I guess this is getting a question of, so how much of the information or knowledge do we want the model to simply learn from the data versus building the model architecture? So I suppose if we use character-based models, you need more data to achieve similar performance, or is that true?
Yeah, so yes and no. So the one issue people have run into, including myself, is that when we look at the sentence as a sequence of words versus a sequence of letters, sequence of characters is just suddenly is so much longer. So it takes much more compute or the time to process the whole thing. So often it's a computational bottleneck we run into, even if we have the same amount of data. But there was a paper from Google Montreal showing a couple of years ago, showing that if you spend tons of, let's say, compute, which Google should do for the benefit of humanity and scientific community, so they did it, and it turned out that the character level models do work as well as word-based models with a similar amount of data. And then when the amount of data was smaller, actually, it was more of a mixed result. It was not necessarily the word-based model was better. Yeah. Not sure why that is. Probably because some of the words becomes suddenly so rare that the model can't really learn from a small corpus, perhaps.
Yeah, that's interesting. Right. I think maybe I can share some of my experience working with dialogue agents. So I think when I first started working on dialogue systems, I wasn't trying to build any complex systems like Alexa or some social chatbots. We were constrained to a very simple setting where, the game is like you have two agents who are trying to find their mutual friends. And the things they talk about are extremely simple. We have maybe 100 names for people, and then they went to different colleges, they work at different companies, and the two agents are going to exchange such information to find their mutual friends. But then soon I realized that even within such a simple environment, there's like 3 attributes they have to talk about. The different types of the variations in expressions is still huge, so that we cannot handle all the different ways of saying the same thing, especially when the model wants to express conjunctions of different attributes. So then this involves some logical operations. And then I realized that no matter how much restrictions we put on the word we have, like the easiest one I think people have worked on is the blocks word. You just talk about triangles, cylinders, several colors, and the position of these objects. But still, because of the compositionality in language, there are so many different ways you can talk about these things. And it's still quite challenging for machines, even in such simple words. The other thing that I didn't appreciate much before I started working on NLP is the subtlety of meaning. So sometimes even a single word can change the meaning of the sentence. So remember when we worked on the pun generation project. So when we were just looking at the outputs, we're trying to tell which of the outputs are more funny. And I forgot the exact example, unfortunately. But remember the one example. There's a single word which is actually. And that word can change the meaning of the sentence entirely, because once you have actually there, that means that you assumed you didn't expect something to happen, but then it happened. So that changed the whole thing there. And then I realized, okay, so for these subtle meanings, I don't really have an idea of how our account model can capture these things by just learning on tons of data without additional supervision or additional interaction with people.
Yeah. So if I just add one quick thing is that this is the reason why I really hated year 2017 when every single master student at NYU knocked on my office door and then told me that they have idea to make GANs work for natural language text generation, and without realizing that you can't really compute the derivative or gradient when the input space is discrete and the length or the size of the space changes. That just reminded me of this. Yes.
Right. The GANs got a lot of popular around 2017, but I think there are papers showing that they don't work better than standard language models.
Yeah, I mean, you can compute the gradient, right? When the variable is discrete, and then none of the students actually realized that until I just told them, now can you write the gradient on the whiteboard for me of this variable where x is a discrete variable? And everyone was like, this, no. And then they all left.
Yeah, I guess students tend to get attracted to more fancy techniques. Actually, even last year, I have students in my final project working on GANs for text generation.
Did they pass the course?
Yeah, they did. I think it was a lot of effort anyway, even to make that model train.
Right, go ahead. You're gonna.
Yeah, I was just going to jump in and say that I think it's really interesting to think of, you're talking about puns and humor, right? And that's if you want to focus on, the true understanding of text, I think humor is probably like one of the most subtle ways of doing that, right? It's one of the, in order to get humor right, you need to have a very accurate model of what you're saying, how you're saying it, and also the mental model of the person who's doing the receiving, right? And so it's really it's really focusing on a different. I think it puts the game up at a much higher level than sort of just like understanding like who walked into the room and did what. You need to sort of understand their mental model. Yeah.
So, João,
right, there are definitely lots of social and cultural.
Does that ring true to you, João? Because and on the one hand, you send Wikipedia into a transformer, and it can generate pretty good text. On the other hand, it's not conversing. I mean, is that what is really missing? Is that why you guys are interested in the conversational aspect? Is because it brings a new challenge that is specific to language?
Well, yeah, I mean, I can say at least, my interest in it really spawned from the fact that, a lot of language is about communication, and much of communication is about communicating with other people, which does make the task that we're trying to do a lot more complicated. Oftentimes what we need is two, like we were just talking about, a mental model of a person. And this does challenge neural networks in a very specific manner, meaning that suddenly we have to, actually encode information that is not just vectors that can represent something in a latent space, but also now actually build representations which are meaningful situationally. And that to me is like super, super interesting, and also obviously extremely challenging. I think that when you're doing, not to knock on translation, but when you're doing translation, there are shortcuts that can be made that don't require like necessarily having as much meaning representation there, right? Whereas I think when you're starting to talk about dialogue and you want to do a complicated task and you want to have the person have fun, then all of a sudden, this opens up a whole new world of problems. I will also, just as a small tangent, talk about something that I think for me has become interesting a lot, and I think it's interesting to a larger amount of the community, which is that the amount of bits that we give to our transformer models versus the amount of bits that come into a child are very, very different. And to some extent, I think one of the large challenges that we have at the moment is understanding, there's these new papers on scaling laws for language models, and trying to understand, like, if you look at the scaling laws for people and scaling laws for language models, they're very far apart. And, part of that could be architectural. Obviously, Brad knows a lot more about that than I do. But it's still an interesting challenge also in terms of understanding, like, what does it require, to learn and train these agents with. Maybe we need to go multimodal or something, but it seems very strange that we need, trillions of words in order to train these models.
Yeah, it's on the vision side. It's been interesting that for a long time, it was speculated that the reason the vision models aren't doing better is because we don't have data sets the size of what a human experiences like within the first few years of life. But now the vision data sets are way bigger than what a person experiences in some cases in their entire life, right? And we're still running into the same problems. So we've sort of solved the data set size problem, and we're now seeing what other issues remain, at least on the vision side. And I guess, yeah, it's clearly true on the language side as well.
Do we know what language is for? Isn't it for getting things from people? Isn't it for advancing our own agendas so that we can mate and etc.? I want someone to disagree with me, by the way.
I'll disagree with you. I think language is about, we go through life and we build models of the world, and language gives you the ability to transmit your model of the world to other people. And that's crucial for inheritance of ideas.
I'm happy to be more cynical than that. I think that's a way too optimistic, angelic vantage point. What do you guys think?
So I have actually one thought is that one small sub area that I worked on for a couple of years is called emergent communication. That is where we assume that we have multiple agents that are trying to solve problems either collectively or they compete with each other. And then what we do is that unlike usual multi-agent system, let's say simulations, we give them a pretty rich high bandwidth communication channels. But of course, we don't really designate any protocols in advance. They have an option to evolve or to develop their own communication protocols. And then one of the goals there is to see if these agents collectively can explore the environments better, collect more richer set of experiences that can be shared in order to solve the problems better or compete better against the other set of agents. And then the reason why I brought up is that in one of those workshops, so we are organizing your workshop on emergent communication and neuroscience over 2 to 3 years. And then at one workshop, we just randomly invited Jürgen Schmidhuber. And then Jürgen's first, remark was that I don't know what is so special about emergent communication because, from his perspective, every layer of any neural net is developing a communication protocol to talk to another layer that is adjacent to each other. And in particular, in recurrent network, that's even more interesting because layers are talking to each other of a different copies from the different time step. So in that sense, perhaps this is even more cynical than Paul. Your take is that perhaps the language is really nothing but just one layer or the shared weight across all those neural nets that we have in our head. Maybe that's about it, right?
But language is supposed to be the most special thing in the universe, in our universe, but it separates us from the brutes. It's supposed to be the highest abstraction and involve all of our other cognitive abilities merging into an abstract representation. But that's why I'm wondering is like the language models that you guys are working on and developing, does that jibe with your experience, or is language not so special?
I'm actually known to say that meaning is overrated. So
all right, you and me, we've got to go have a beer sometime.
Yes, we should.
But there's still a lot language is missing, right? With the conversational agents, I think that really jumps out at you. Is that correct? Huh?
The models, I think right now we don't really have a good way to evaluate if these language models understand language. I mean, they're good at solving the practical tasks we want them to solve. But then for more challenging tasks, like communicating with people or understanding humor, I don't think or even for standard tasks, you want to, like Brad and Kyeonghyun mentioned about this computational generalization. If you want to go out of your training distribution, these models are very brittle. So it depends on, if we just want them to perform a specific task, then maybe the current models are sufficient without understanding meaning and whatever meaning means. But I don't think we know how to evaluate how well this model actually understands language like humans do.
All right, we're getting close to time here, but I have two more things I would like to ask, at least, and I don't care how long we go. But one, attention, and Brad, this is kind of directed toward you, pitting you against the rest of the panel here, I suppose, because you've worked on, I'm putting in air quotes, attention in, as we know it in psychology and in neuroscience, or as we don't know it really, in many respects, or as we think we know it, and different kinds of attention. And then Kyeonghyun comes along and makes this model that you didn't call it attention, right? It got
we didn't.
Right, and then it got the label attention later, and now has NLP usurped the word attention? And what? So the NLP panel, folks, are you guys happy with the word attention? And I'm going to let Brad start if he's happy with the word attention.
So I think, I guess my controversial take is that attention, as it's used in the context of transformers, is exactly the opposite of the way that we typically think of attention in cognitive systems, right? So attention in transformers, as I understand it, is a thing that is learned, and it operates in a very specific way depending upon what stimuli are coming in. And in that sense, and it also operates in parallel, right? And so in that sense, it's more akin to what we in the cognitive side would call an automatic process, something that kicks in when particular stimuli, hit a series of particular representations in a specific way. And a whole bunch of things can happen really fast in parallel. Whereas when we think of attention, or at least when I think of attention in the sort of canonical mind way, it's what's called a controlled process. And a controlled process is exactly the opposite of that. It's effortful. It's very flexible. You can control it, but it's also slow and it cannot happen in parallel. So, again, it depends on your definition of attention. My personal definition of attention is actually from the biology brain side is just simply deciding what information to discard. That's my definition. So that includes like a whole lot of things, obviously. But it's so broad as to be almost useless in this discussion. Whereas when we're talking about, I think, attention and the sort of paying attention to something, right? It's the sort of controlled, monolithic, monotonic process.
Yeah. So it was 2014. So we got this. So Dima Badenow, the first author of the attention paper, came up with this brilliant idea. We implemented it. He ran all those experiments. We did some analysis, and then we were like blown away because it worked so well. So we started writing a paper.
Can I stop you real quick? Because I was going to ask you this, so I'm just going to ask you, because you toiled over language models for years with with plenty of progress, right? But then to come along like a breakthrough like this, where the way you tell it, when you saw the idea, you immediately saw that it would work and it would just be a matter of implementing it. And so that's kind of like a breakthrough. But is that a lesson to just keep pushing forward and serendipity will happen because those moments do happen? What's the lesson there?
So I think the lesson is that, of course, getting a good student always helps. Like having Dima as an intern at Yasha's lab was just the best move ever. But one of the things is that it was in some sense bound to happen because we knew what was missing, like mathematically. So that was the time when we all knew why LSTMs or GRUs were really important, why the residual connections were really important because of the vanishing and exploding gradient issues. And then we knew that as the size of the input changes, the network's capacity needs to adapt to it. And we knew all those things. We just didn't know how to address it in the most concise or the most succinct way possible. So in a sense, this particular concept of attention, in some sense, was like right around the corner, but we just needed one or two extremely bright people to notice that and then just take us, around that corner. And of course, the Dima's initial explanation did not have a word attention. I didn't think of attention either. We kind of wrote a very quick draft. And then after running all those experiments, and then Yashua looked at the draft. And of course, Yashua was extremely excited about this whole idea. He made all those edits. And then only edits that I could see, the major edits I could see was that he essentially put the word attention at every set paragraph.
It's his fault. Okay.
Yeah. And then I kind of, went back, reverted it back, every single one of them, except for I think the one where there was some kind of referral to some examples there. But yeah, I totally agree with Brett in the sense that it's not really the attention that we think of in the cognitive science or the neuroscience, in the sense that the attention often is there for the kind of sparse processing of a very, let's say, high bandwidth input. If you think about it, the original or the more widely, let's say, thought of attention. On the other hand, this attention is extremely dense. It has to look at every single possible input and then determine which is important. However, after a few years, now everyone is anyway calling it attention. So I started calling it attention. It's a very catchy name to start with. But what I'm realizing is that it's just what computer scientists have been doing all along, is that it's just a separation of the concept or the idea and the implementation. So the conceptually, it is attention in a sense that we're trying to decide what is the important parts, we use it. But for implementing it, we've been using all those, let's say, extremely dense parallel computation, because we know that kind of implementation enables us to use this set of, let's say, algorithms such as backpropagations as they are, without having to make substantial changes. So yeah, that's why we didn't call it attention, although I almost feel like we should have, now that I think about it, but well, I didn't know.
João, He, do you guys want to weigh in on this?
Yeah, I think, it's, in some sense, we could sparsify it. There's work on sparsification of the way that the attention mechanism works, mostly for efficiency, right? I agree that completely that what we're doing is, some high level inspiration with, an implementation that is for, the hardware that we have, right? In some sense, that the fact that we're doing things differently than the brain is supernatural because our hardware that we have is completely hardware or wetware is just very, very different. And, I think indeed that one can say that the inspiration behind attention in a transformer is in fact sort of kind of similar to actually focusing on certain parts of, the input sequence, right? The thing that I would agree with on Brad's component is that in large part, the way that we use transformers, the actual mechanism for paying attention is fixed once you have training data. So any new input, what we have is that, that input is fixed. And so there's no computation or change that happens, beyond that. But yeah, I would say, my wife is a neuroscientist and she completely disagrees that it's anything like attention, real attention. But, I definitely think that the inspiration is certainly, similar in terms of what we're trying to do with the model.
So when I think about human attention versus machine attention, one difference I think is that for human attention, it's more explainable. Like I can tell I'm paying attention to this part because I think it's important for my task or reasoning process. Whereas for, maybe there's some disagreement. I guess other people can weigh in. But for machine attention, I guess it's more about, okay, I mentioned maybe make the optimization better, or it enables interaction between different parts of the input. So I think from the explainability perspective, there's this difference between human attention versus machine attention.
Yeah, I'll emphasize that there's sort of two different ways that attention can be used in the psychology side, right? And I think you're absolutely right on the explainability side when we think about the one form of controlled attention, right? But sort of my broader definition of just throwing information out is actually much more similar to the Transformers version, and I think in that sense, Joshua was right on the money to call it attention in that sense. So yeah, there's two different definitions. Most people refer to the controlled version on the psychology side.
Guys, we're almost out of time here, so I would love to go around and ask you a terrible question here. What I want to know is something that you're working on right now that you're really struggling with, that seems just out of your reach, that's frustrating you, that you can't quite grasp. Zhao, you want to besides your wife being a neuroscientist, do you have something else?
It's a good question. I think that a large component of what's sort of bothering me, it has continued to be like how to, take the modern neural systems and make them effective in like a real life setting, right? We have all these beautiful generative models, and, because of their toxicity and their controllability, no one in an IRB setting would allow me to use, an internal review board where they're going to tell me whether, I can have patients talk to a generative model would allow me to actually do this, right? Mm-hmm. I can't get permission for any of the healthcare stuff to use these beautiful generative models. And the thing that I'm struggling with at the moment is how to reconcile the fact that we have all these very, very powerful models, and yet in terms of practical use and application, they're really, really hard because we have all these safety, toxicity, explainability problems that stop them from being able, to actually go that last, half mile.
Okay, very good. Who wants to go next? I'm going to let you guys jump in. Who feels the most frustrated?
Wait, did you think that the Joel felt most frustrated? Is that the reason why you asked him first?
I have to roll a die to choose. I was feeling his wife neuroscientist pain,
I see.
I can go next. So one thing I'm working on is how to make this language understanding models to generalize to out of distribution data. So we know that if you train the model on specific data set, the model is going to work well on data that looks similar to your training data. But it's hard to make this model generalize to new data that's still from the same task. So I think one challenge here is that it's unrealistic to expect that this model can generalize to arbitrary distribution. So you have to give the model some knowledge about what your test data is going to look like if it is not from your training data set or training data distribution. And I find it's very challenging to find a balance between how much prior knowledge you want to bake in versus how generalizable this method really is. So I feel I have some ideas, but I don't have very good satisfactory solutions to this problem.
Well, how about one more NLP, and then we'll finish with the neuroscience.
So I'm at the research is always struggle anyway. So, but the one thing that I'm struggling at the moment, besides science, is how to convince my graduating PhD students or the outgoing postdocs to consider a career that is outside FANG, let's put it like that, or the outside Google brain, the Google DeepMind, Facebook AI research, and Microsoft research. Because I don't know, I feel like too many people, too many brightest minds are just going there. I mean, the compensation is great and so on, but I do feel like all these NLP algorithms, machine learning algorithms, can be used for so many interesting problems and important problems. But I feel like too many people are just being sucked into one of these 5, let's say, tech firms, and the marginal impact on the society coming out of these individual PhDs is just converging towards zero. So I'm actually struggling to convince them to see beyond these tech firms, but it's an uphill battle just because of the tech rally that is never ending. The compensation looks just so much larger than before. Yeah.
But this is kind of related. So when you started your postdoc with Joshua, he gave you 4 options for what to study, and the third one was machine translation. And I don't remember if you struggled to accept that. I don't remember, whether that lit you up or whether you really, thought about it a lot or whatever. But that was back then, and now everything's NLP. That was back then when NLP wasn't working, right?
NLP wasn't. Yes.
Yeah. Right. Okay. Machine translation wasn't. But So I thought what you were going to say is that you struggle to convince your students to do something besides NLP or besides language-based approaches, because that's the that's
true. That's true as well. Yeah, it is a bit implied. I mean, in a sense that the NLP is popular because all these, let's say, tech firms are insurance service firms, and then the NLP is kind of very obvious and immediate area they want to invest in anyway. And then you have and probably because of that, my students are being recruited by these companies with a high level of compensation, which is great. But I want my students who are really, really bright to do something beyond what I've done or what people in our generation or the previous generations have done. But it's an uphill battle. I haven't convinced any of them, except for one student who joined Tesla. That was the furthest away from the tech firms, and then it's not that too far.
No, yeah. All right, so that's a very career-oriented struggle, which is fine. Brad, you want to round it out?
Yeah, sure. I've got a struggle that's been ongoing for a while now. Over time, I've come to view attention, and I mean the sort of controlled process version, as being something, rather than helping us perceive in the moment by just dealing with information overload, it is actually something that helps us to structure the sort of data set that we're building about the world. So it's there to help us learn better for the long term rather than help us function better in the moment. The problem is that I have no way to test these theories, right? Because I can't alter the way that attention works in infants and then see what goes wrong, obviously. So I'm basically stuck where I've got this theory but I can't figure out a good way to test it.
Oh, man.
Apart from like building simulated agents, but there's still 1,000 other problems there. So that's my problem.
So I lied. I have one more quick question. Brad, I'll start with you real quick. So I've heard Kyeonghyun say that we're at the very beginning of natural language understanding, natural language processing machine, all the language-based stuff. We're at the very beginning. It doesn't feel like that. Where are we in vision and in the associated cognitive processes? Are we at the beginning? It doesn't feel like it.
It doesn't feel like it, but I think that when we finally get there, wherever there is, we're going to look back and realize that this was still the beginning.
Yeah, that's sad, isn't it?
Yeah, there's just so much we don't yet get about how vision works. I mean, categories from images is such a slim sliver of what the human visual system accomplishes when we look at something. Even in just like 200 milliseconds, we just like instantly apprehend all of this context and information. And I think we're still a long way from doing that. So I guess we're like at maybe like a 5-year-old level of understanding.
All right. What year level are we in language, guys? And are we at the beginning?
We're at the beginning for sure. Yes. I mean, He and João were able to actually tell us all the things that don't work. And then as João pointed out, we can't even get the institutional review board, who often say yes, as long as we write the proposals correctly, to say yes to just having it talk to the patient or the subject in a very controlled manner. So we're very, very far away from, saying that, here's the actual language understanding or generating, models, right? And then, I think that you gave an example of learning 3 words was difficult, I guess.
Yeah, the sometimes colors, single word changes. Yeah, in the blocks world. I guess that's what people worked on at the beginning of the AI, and we're still struggling with it now.
Agree, João?
Yeah, no, I completely agree. We're at the beginning. I think that, this is, there's so many open questions, and, I don't think that 1 trillion parameters is going to solve it. I think that, the real, we have new breakthroughs that we really do need to make in terms of, trying to be able to actually interface with people in a manner that is productive.
All right. Well, this is great. You guys are at the beginning. We collectively are at the end, actually. See what I did there with the actually? By the way, it was Tony Movshun who used the cottage industry vernacular for like the small labs. Just to wrap things up. So thanks, guys, for the wonderful conversation. I really appreciate it, and I hope that students get a ton out of it.
Thank you.
Thank you, Paul.
Thanks for hosting.
Brain Inspired is a production of me and you. I don't do advertisements. You can support the show through Patreon for a trifling amount and get access to the full versions of all the episodes, plus bonus episodes that focus more on the cultural side but still have science. Go to braininspired.co and find the red Patreon button there. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.
The